Okay, Assalamualaikum warahmatullahi wabarakatuh. So we start with this chapter number 4, molecular association. Okay, so I don't know uh, where we stop. So I will start again with this molecular association. Okay, so as we know that the objective of this chapter is that we want to know how molecules interact with one another. Okay, so we have, let's say we have male and female, so interact maybe with couple, or even cell and virus, so how they interact, or the protein, in this case protein and ligand, so how they produce the complex. Okay, and then we are going to examine the thermodynamic or the temperature effects and the mechanical effects of the association. Okay, so it will affect the chemical association. So what we assume here is that the force that control association are usually non-covalent. For example, the electrostatic, van der Waals, and or hydrophobic force. Okay, and also the second one is the association are stereospecific, meaning that we have a lot of space in the protein or on the protein, but the ligand only can uh, interact with a certain part of the protein, the log and key. So let me start. So if we have two molecules A and B, or male or female, or protein or ligand, so in a solution, so you can associate to become the C, the complex, with a certain constant, okay, or a constant, so we can get this equation A plus B becoming C, or C dissociate become B and A again. Okay, so using uh, the reaction, okay, so we can measure the concentration. So for this one, we measure the concentration of this C, the production of complex. So we dc dt equal to alpha A B minus B and C, and A become at equilibrium. So dc over dt equal to 0. Then we can get 1 over 1 over k dissociation is equal to the C over A B concentration. Okay, so then we can know how fast it will dissociate or how fast it can associate. Okay, so we have this dissociation constant and association constant. So when K association higher ligand greater than 0, then we have the higher ligand Fa. Okay, or it can attract more friendly to become the complex. Okay, so if we see this, how fast or how much the A and B or B associate with A. Okay, so the fraction, so we can have from this equation F equal to L over L plus K dissociation. So we can get that using the only the ligand concentration, so we can get how many ligand already attached to the protein to become the C or the complex. Okay, so if we can plot the graph F, or in this graph is theta against the concentration of ligand L, so we can get this type of graph. So at K, the fraction equal to half the fraction, so we can find the K dissociation. Okay, so this one of the way we can find the K dissociation. So again, let's like before. So what we can know about this Hill equation. Okay, so we can increase the fraction increase smoothly. We increasing L starting from 0 and approaching 1 at high L. Okay, So 0 where no association, until 1 uh, all the reaction center or the the ligand or the protein has been attached by the ligand. Okay, and the point where half of the site are occupied is L, that the C equal to K this. So we can find the K dissociation easily using, if we do the experiment. Okay, so how the, if we have a lot or if we have more than one binding site, okay, the binding site, so how it affect the cooperative of, or how the ligand attached to this binding site. Okay, so here we have the concerted binding, sequential binding, and there is never interaction. Okay, so concerted binding, all are at one, all the ligand attached to the binding site in one go, and discrete binding one by one the site. And the nearest neighbor interaction, if we have so many binding site, so the nearest neighbor will affect the binding of the next ligand to the protein. Okay, so these are the concept of binding. So if protein have an N binding site, so let's say hemoglobin for binding site, so uh, this interaction, all binding site to be either simultaneously occupied or simultaneously empty. Okay, semua semua bind ataupun semua unbind. So the process is P naught plus NL PN. So P naught is protein with empty binding site, and PN is a protein with all site occupied. So again, using the equilibrium condition, so we can get Pn over Ln P naught equal to 1 over Kn. So where Kn a compound dissociation constant, reflecting the constant binding of all n ligand. So the Hill equation for this constant binding, okay, so we can prove it. So F equal to Ln L to the power n plus all L to the power n plus Kn. Okay, so if we plot this, so we are going to get uh, this type of plot. So we have the high affinity. So this one will be much faster to be the binding. Here you can see that. Here we can say that these are the concerted binding, and these are the next one, the sequential binding. Okay, so uh, all ligand attached at the same time to the protein. Okay, so here is the characteristic of this graph. So n equal to 1 where the cursor curve is steeper in the middle than at the start. Okay, so we can see that. Here we can see that these are the cooperative concerted binding. Okay. Okay, and if we rearrange this Hill equation, okay, so in our textbook is equation 4.8, but that equation is wrong. Okay, so you can check it. So these are the correct one, ln f over 1 minus f. So if we plot this, so we are going to get this equation, we are going to get this Hill plot. So we can see that these are the hemoglobin and myoglobin. Okay, so high affinity state and low affinity state. So we can see that here we can say that n equal to 3. So these are the more cooperative. So this one only one ligand attached to one binding site of the hemoglobin, but here we can see that here 3, even though there is 4 binding site for the hemoglobin, here at least 3 ligand attack or attached to the hemoglobin at one time. Okay, so what we know, the Hill plot is, this Hill plot is used to evaluate cooperative. So we can see that for hemoglobin N at 3, and the value of N obtained as the slope of Hill plot is referred to as the Hill coefficient. So if we see that here, we can play with the number N, and we can see, or we can guess how many binding site there is at on the protein, okay, or the unknown protein. So and for N is equal to 1, so there is no cooperative. So all the ligand can freely bind to any site of the protein without attacking uh, or 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 attach it to the binding site in one group or in one group. So NH equal 3. So these are the maximum cooperativity. So meaning that in the hemoglobin example, so 3 ligand will attach to the binding site, or the 3 binding site at one time. But here, this next one is the sequential binding. So in reality, hard to also fully constant binding. So we are not going to see this constant binding. So there is more general equation. So binding to different site on the protein is not concerted but sequential. So P1 protein attach one ligand become P1, then another ligand attached to P1 become P2, and another ligand attached to P2 become P3 until so on. Okay, so solving this equation or finding the equilibrium, so we can write the equilibrium condition is equal to this equation. So so the Hill equation, solving this f, the fraction for this equation again and again, so we can get this Hill equation. Okay, so what we can say about this equation is that so it cannot rise steeply as ln because all the term in the numerator with lower exponential. Okay, so this one will affect the uh, how the speed of the uh, all the binding site to become one, or all binding site to be occupied. Okay, and intermediate state of receptor occupancy reduce the significance of the saturation. Okay, so let's say we have one binding site already occupied. So the next ligand need to find the other free site to bind to the protein. Okay, so this one will uh, reduce uh, the speed of the binding. Okay, or not the speed of binding, but the speed of all the binding site to be occupied. Okay, and here the lower the value of n, that will be determined. Okay, so here you can see that if we know, if the protein has 4 binding site, but if the binding site is near to each other, so the next ligand need to fight with the rest to uh, attach to this binding site. Okay, so it will be a lower value. Okay, and estimated determined Hill coefficient must be less than or equal to the number of binding site. Okay, so here as we see, less than the binding site if that the binding site near to each other, and if the binding site is far from each other, so we can get the equal number of binding site, the ligand to attach to this binding site. Okay, so here these are the example of association and dissociation of O2 from hemoglobin. Okay, so we can get this. So we can have other like this graph, or we can have as this graph. Okay, so meaning how fast it will be attached to this hemoglobin. Okay, and the next one is the nearest neighbor interaction. So if we have a very big binding site or large binding site and a long protein, so many binding site, so the next ligand will attach to the next uh, binding site. So let's say these are all the binding sites, so we can see that. So here we can see that the ligand will quickly bind to the next neighbor rather than this lonely ligand. Okay, so we have K0 for the binding of isolated ligand, and K1 is the binding for the adjacent to the occupied site. Okay, so these are from our textbook, figure 3.8. The binding curve will be more similar if the ligand bind more tightly in the presence of the marine ligand than in its absence. Okay, so here we can see that if we have the neighbor, then sigmoidity will be much steeper rather than this one and go to. So linearing the what we can say is also there's linearing the molecule will increase the number of sites and increase the significance of the binding curve. Okay, so it's easier to bind to the next neighbor. But if we do the synthesis of the protein, so if we increase the length of the molecule beyond the average length of molecule, so we will not make binding significantly more cooperative. So let's say we have uh, ligand binding here and ligand binding here. So the ligand, uh, the free ligand need to diffuse to find the ligand here and this ligand here. So it will be much slower for the all the all the binding site to be occupied. Okay, so next we want to see the association strength. Okay, so berapa kuat uh, association to, or in the female male and female. Okay, let's say male and female become a couple. So how strong is the couple? So can easily become back male and female or still in the couple uh, situation. Okay, so here we have two. So how can we know the association can be dissociate or not? So we see the thermodynamic of association. So what are the effect of the temperature for to that association, and then the contact formation of the association. Okay, so we can see how it contact the force that react to that association. Okay, so first we see the thermodynamic of association. So here, so again, the non-covalent contact that stabilize the complex. So finding the free Gibbs molar energy. Okay, so in the solution, so we can see that delta G, the free Gibbs energy equal to this equation minus RT ln PB over LPF or RT ln K dissociation. So we see, or we when we measure the when we do the experiment, we measure the free Gibbs energy delta G naught. So what happens if delta G naught greater than 0? So whether this is easily dissociate C from C to A plus B or associate. Okay, so whether it easily dissociate to A and B or still in the C complex. Okay, okay, so that is the one of this thermodynamic association. Okay, so what are the contact information? Contact information that affect this one. So here we see that again this non-covalent force, hydrogen bond, salt bridge, or hydrophobic surface. So all give the distribution to the free Gibbs energy. So if the I contact with energy epsilon I, then the concentration of contact to the binding energy be affected by the sum. Okay, there is delta G. So epsilon I. So let's say epsilon 1 is from hydrogen, epsilon 2 is from salvage, and epsilon 3 is from hydrophobic. So we add all of them, so it becomes the free Gibbs energy, the total free Gibbs energy. Okay, so what we can, where we can get the value, so we can get from for hydrogen bond from table 2.1 and 2.2 from our textbook, and from the Lennard Jones potential. So we have electric force epsilon less than 0. So epsilon less than 0, so derive the association. Okay, epsilon greater than 0, so we have the dissociation. Okay, dissociation will be higher, meaning that in this equation. Okay, so put it here, so we can get K dissociation. So what we assume here is that ignore possible dissociation of structure of the two molecules brought about by the association. Okay, so meaning that if the protein is in L shape, so when it bind with the ligand, it's still in the L shape, not uh, K shape or M shape. Okay, so we also ignore the small stretching and twisting distortion of the bond within each molecule or larger molecule. So we assume that because distortion effect raise the free energy of the complex and oppose the association process. Okay, so we ignore that so that it will not distort the effect. So, but as we can see that there is a lot of force, okay, and some of the force will distort the protein configuration or conformation. So we need to get the, if we want to get the nice curve fit of our experimental value, so we need to add more term or more epsilon term in this value. Okay, so we need to add so many force that uh, we think will affect this free Gibbs energy. Okay, and we can also see that when two molecules associate, here the last decrease in entropy due to the motion of the two molecules with respect to each other. Okay, so these two molecules or this new complex will react differently with the temperature. Okay, so next is the mechanics of this association. Okay, so what are the effect of this mechanical uh, value or the mechanical movement of the complex? Okay, so here we can see that we, from our statistical thermodynamics, we have the partition function of the molecule Q equal to QCT context, intermolecular context. T is translational, R is rotational, P is positional, CF is combinational probability, and S is the solution effect. Okay, so here we can see that we can also find the K dissociation. Okay, K dissociation constant by modifying or calculating all these partition function. Okay, so we can get these three. Okay, so these are the first one, intermolecular context. So the partition function is equal to QCT CCT over QACT QBCT equal to N C over NA and NB. Okay, so here we can replace QCT in the previous equation with the number of molecule A, B, and C. Okay, so this one from our stereochemistry. Okay, so we can find the number of molecule that uh, react with, let's say, A react with B to become C. Okay, so we can put it, so we can get this contribution from intermolecular context. So next is the translational free energy. Okay, so A can move around in the solution, B also can move around in the solution, C also can move around in the solution. Okay, so the translational partition function for molecule in volume, we can say Qt equal to V 25 mkt over h bar squared over 3 cube. So these are 3D. Okay, or V equal to V, the volume, or over the uh, kappa number cube. Okay, so these are thermodynamic wavelength unit length. Okay, so we calculate for each molecule A, B, and C multiplied by the Avogadro number, so we can get these are the thermodynamic. So what we want to say is that to find the contribution from this transitional free energy, so we can calculate the thermodynamic wavelength for each molecule multiplied by the Avogadro number, so we can get the conversion for this uh, partition function for this transitional free energy. Next is the transitional free energy. So we have QR equal to pi half 8 pi Ix kt, Iy kt, Iz kt. So where Ix, Iv is the moment of initial for rotation. Okay. So again, we put this for each molecule A, B, and C. So QCR over QAR, QBR. And if C and equal to A, so the protein, the ligand is too small. So when we test for to A, it nearly the same, the shape of the molecule. So we can see that this one cancel, QCR cancel with QR, so we only have one, or we can just calculate for QBR for this partition function for this partitional free energy. So next is all the molecule will vibrate and all the binding site also vibrate, or the, let's say, hydrogen bond also vibrate. Okay, so we can find the partition function for this version of free energy as for harmonic oscillator. QVI equal to exponential minus h nu I over 2 kt over 1 minus e epsilon exponential minus h nu I over kt. So where this nu I is conventional frequency, pi mu I, the force constant, and the reduced mass of this A and B. Okay, so if we assume that these are the non-covalent constant contacts that hold the two molecules weaker than covalent bond. Okay, so it can diffuse or cut out of this non-covalent bond. So here the Western frequency for this big non-covalent contact will be low, so H nu less than kT, so it effect by the temperature, the thermodynamic kT. So if we can expand it, exponential minus h nu over kT equal to 1 minus minus h nu over kt and put back into this equation. So we can get qvi equal to kt over h nu I, or equal to kt over 2 pi h square root of pi over mu I. Okay, so what we need to know, or we do the calculation for this partition machine, is that change the temperature, the constant, we know the constant, this force constant and the reduced mass. Okay, so we can get this uh, partition function. Okay, so here what we can say is that for tightly bound water molecule, the strength for the contact holding the water in place might be really similar to the contact formed by the same site when binding to a ligand. So which one protein will associate to? Okay, so we have whether protein will associate with the H2O, or the protein will associate with the ligand. Okay, and which binding will produce the most entropy. Okay, so it does not like entropy, so it will uh, either protein bind with water or protein bind with the ligand. So dissociate the entropy. Next is the solvent that we use. So it will also affect the partition function of the complex, the A plus B becoming C, or C becoming A plus B. So here we can see that the liquid water is 16.7 kilocalorie per mole per Kelvin at 298 Kelvin. So in the type of crystal, 10 kilocalorie, 10 calorie per mole per Kelvin. Okay, so the variation of a water molecule within a crystal. So at 298 Kelvin, the free energy used to replace the most tightly bound water molecule is about 2 kilocalorie per mole. Okay, so there is free energy cost of 2 kilocalorie per mole for immersing water at the space of protein is much less than that of immersing a ligand at the standard state. Okay? So the much lower entropy cost the immersing water would strongly favor the binding of the water. Okay, so rather than binding to the protein, it will bind with the water. Okay, and a ligand that displays only one water molecule will not be competitive in binding. Okay, so meaning that with the depend on the solvent, so it will be much difficult for our ligand to bind to the protein if we have let's say for the water, so you need a lot of energy to cut the binding of the water to the protein so that it can bind it to the protein. Okay, and if a ligand is large and replaces several water molecules, so bring 10 water molecules could increase the entropy free energy by 20 kilocalorie per mole. So in this case, entropy favor the binding of large ligand. Okay, so A plus B, so it become more. A plus B become C, not A plus water become C water. Okay. Next is the computational free energy. So here, uh, what we can say is that solution can produce large computational chain. So from L shape to let's say K shape. So when small molecule bind to proteins, reaction in the small molecule are really not considered because small molecules do not have mass activity. So the protein still in its shape, not modified shape. On the other hand, protein sometimes they large combination chain when they bind the small ligand. Okay, so let's say this protein from L shape from L shape becoming a V shape. Okay, so it change the conformation configuration. Okay, and A portion of molecule may behave like a random coil per association and be forced to assume a single condition after an association. Okay, so here you can see that the random coil, so like say the L shape, but when it bind with the ligand, it become the B shape. Okay, for example. So here the entropy of solution. So when delta S equal to 0, S interpret as rigid body solution, hardly any conformation change. Okay, so L shape, if the protein is L shape, so A is L shape, so C also L shape. Okay, but if delta S greater than 0, the entropy is higher, so we are going to have a change in combinatorial freedom. Let's say A is an L shape, but when it bind with the ligand, it become the V shape. C become the V shape. Okay, so if we factor, so what we can say here is that the association constant or the dissociation constant K dis or K associate can be measured or calculated using the concentration, the first one, the equilibrium, the statistical thermodynamic 1 over Ks, or the statistical mechanic calculation using the partition function. Okay, and then at least three type of binding association. Okay, so this we can add more, but here we can just say that these are only the hydrogen bond, the hydrophobic bond, and the other one is, so to reduce the error, or to get the nice curve fit, so we need to add more term in the formula. Okay, so in order to get the more accurate dissociation constant. So that's all. Thank you.